Welcome back, everybody of you who did come back for the last lecture in this series. As you remember, the first time around, we did some sort of very general overview of this area, and then I told you how to prove a lower boundary in size and resolution in as simple way as I could think of. Then yesterday, we did a discussion of this important concept of automatizability or automatability of proof systems, and we devoted most of the time to proving a recent major result by Atserias and Miller that assuming P doesn't equal NP, resolution is not automatable, which roughly would mean that there's no best SAT solver in the class of CDCL SAT solvers. Today I wanted to talk about a different measure of complexity of proofs, which turns out to be kind of interesting, and it turns out to have slightly unexpected relations to other measures, in particular to width. So I decided to discuss it for this last lecture. So the idea is that space of a proof should somehow relate to the size or length of the proof, more or less how space relates to time in computational complexity. And in a proof theoretic setting, the idea is basically as follows. We're doing proofs, right? I mean, a proof is traditionally written on a blackboard. Less traditionally, you can verify it on a computer, say, and you need some computer memory. And the space of a proof is basically how large a blackboard you need, or how much memory you need, so that when you want to make a step, so you can go through that proof using that particular blackboard / memory, so that at any time when you're doing an inference, when you want to derive one line of the proof from some earlier lines, all the earlier ones are on the board. Okay, so a definition is coming up in a moment, but that's the intuition. This was invented and gets advertised sometimes as a way of measuring the space or understanding the space needed by SAT solvers. Space in SAT solving, from what I have heard, is a major issue, a major consideration, although the connection between this notion of space and the actual amount of space or memory requirements that solvers have, I think, is more iffy. It's not as clear cut as the connection between proof size and running time of a solver. So this is like more loose, but it's a nice measure, and it's proof theoretically natural. It's a very good question. I mean, how much space on the blackboard do you need to go through with a proof? Okay, so that's the idea. Here's the definition in the particular case of resolution. So we will present a resolution refutation as a sequence of what we call configurations. So configurations will be, a configuration will be those clauses that are written on the board at any given time, with the condition that you're allowing yourself to have a cheat sheet with all the initial clauses. So the initial clauses, the formula you're refuting, say F, you have a separate sheet with those clauses. You can always add them back. You don't need to store them on the board. So we can present a refutation, say pi, as a sequence of these configurations, where each configuration lists the clauses that are like active in the proof at any given point in time. At the beginning, you have no clauses listed. The board is empty. At the end, you just need your contradiction. So the last line or last configuration in your proof contains just one clause, namely the empty clause. And in between, when you go from one configuration to the next, you do this by doing one of three things. Either you take your sheet of paper with the axioms of F, with the clauses of F written on it, and you copy one of them onto the board. Or you want to do an inference, in this case in resolution, it's just a resolution inference. To do that, you have to have the two premises of the inference on the board. So they have to be on in MI. And then you add their resolvents. So you add what you derive by resolution from them to the configuration. So you have two clauses written up on the board, and you write a third, which you derive from them in one resolution step. And finally, once you decide that something is unneeded, a third thing that you can do in going from one configuration or one Blackboard state to the next one is simply erase one of the clauses that's on the board. Okay, and we measure space as what the largest configuration is in terms of how many clauses it contains. So if a configuration is a list of clauses, the ones that are at the board on the board at a given time, the largest such number, as you look through the proof, is the space of the proof. You might want to say that maybe counting all the symbols, so taking into account whether the clauses are wide or narrow, is a more realistic measure, and that has been studied too under the name of total space. What I could say in defense of this notion is that this one behaves a bit more elegantly theoretically, and there are good lower bounds on this form of space, which implies some lower bounds on total space, obviously, because total space is going to be larger. And there are actually some specific total space bounds as well. So I mean, total space is kind of understood itself nowadays, at least in the case of resolution, not in any stronger system. A space of refutation is how many clauses you have to write at the Blackboard at the kind of most intensive moment of the proof, where there are many clauses on the board. And the space needed to refute a formula F is the smallest space of any refutation of F that you can find. Okay, so that's defined in the usual way. Clearly, you may want to note that clearly space of refutation is some sort of property of the underlying graph, some sort of pebbling space or whatever that is exactly. So that is like length, which is just the number of points in the proof graph, but unlike width, which depends on what the clauses are. Okay, so that's as much as I would say about the definition of space in resolution. I hope it's clear. If not, please ask. And people started proving things about space in resolution somewhere around the turn of the century. One basic fact that was noticed early on was that this is less obvious in the case of width, but space is at worst linear. So if you have n variables and you've got an unsatisfiable formula, you can always repute it in space, basically n plus a constant. I think the constant is actually 1. So this is not a hard thing, that it's not completely trivial, and I think people are a little bit surprised by this at first. Another thing that people noticed early on, like roughly 20 years ago, was that the formulas for which you tended to get space lower bounds were more or less the same ones for which we got width lower bounds. So they started wondering whether there is some sort of connection, and what maybe space is simply more or less equal to width, times a multiplicative factor or plus an additive factor. And the answer turned out to be no. Namely, it is possible to have a family of formulas, say of size n, Fn will have size n, such that you only need constant width to refute them, and you need lots of space. You need almost linear space to refute them. This is in a paper of Ben Sasson and Jakob Nordström. And generally, the first results showing that space can be much larger than width came from Jakob Nordström's PhD thesis. He got an Ackermann prize for that. But that leaves the other direction. The other direction was actually solved a little bit earlier, though journal publication was the same year as this conference publication here. The other direction, it turns out that there is a connection. There is at least an inequality. Namely, this is what Serious Dalmau games were originally introduced for. It turns out that space is more or less lower bounded by width. So if you've got a KCNF and you can refute it in a certain amount of space, then you can refute it by a different refutation completely with the same amount plus just the width of the formula, just the K where the formula is a KCNF. So if you turn it around, this says that the space needed for refuting a formula is essentially lower bounded by the width minus the K that appears over here, okay? So this argument is pretty simple once you've got the gains, and we can do it. So we're proving that the space needed to refute a formula is essentially lower bounded by the width. So let's assume that it's not the case. So there's some formula that that can be refuted in space S, and that space S proof written up as a sequence of configurations is M1 to MT. So each MI has only S clauses in it at most. But on the other hand, assume that there's no refutation in width S plus K. So by what we discussed concerning prover duplicator gains, that means that there is no there's a winning strategy for duplicator in the game with S plus K pebbles. In fact, you could have S plus K plus 1 here, but just we won't care about the 1. You could improve these results by 1, by additive constant 1, but we're not going to care. So what is a winning strategy for duplicator in a pebble game? Well, one way to think about it is as a way of like safe positions or winning positions for duplicator. And if you think about it for a moment, then that sort of set of winning positions in an S plus K pebble game can be seen as a family of assignments. Well, basically a position in this game is an assignment. So a duplicator having a winning strategy means we can think of the winning strategy as a family of assignments, of partial assignments to the variables of the formula F. And this family should have the following property. Firstly, each assignment in it is well constrained in terms of size by prover's memory, so it's at most S plus K because that's how many pebbles we have. Secondly, if this family, this set of winning positions for the duplicator or potentially winning positions for the duplicator is closed downwards, so if something is in this family or in this strategy, then anything smaller is also in this strategy. Then, given a position in which duplicator is safe, if it's not, if it doesn't have the maximal amount of pebbles in it, so if you have an assignment in this family where there are less than S plus K variables in the domain, then prover can ask about any variable that's not in the domain. So for any variable, if you've got an assignment row in duplicator's family, for any variable X, you have to have a larger assignment. Well, possibly it's the same one if X is in the domain, but if it's not, you have to have a larger one still in this family, which decides X. Perhaps you're already forced by what row looks like to, or by the formula, to set specifically X to false, perhaps, or to true, depending on what things are like. But you must be able to answer a question about X. Okay, so whenever you have an assignment that's not maximal size within the family, then you can always extend it by adding a variable to a domain and stay within the family. And finally, well, prover wins if the assignment presented to him by duplicator falsifies a clause of F. So maybe we would have started with this: no row in the family, no assignment in the family falsifies anything in F. So that's what a duplicator strategy is, or that's one way of thinking about it. And we can use that to get a contradiction from these assumptions here that there is a space S, the refutation, but no width S plus K. Namely, we take duplicator strategy given as a family of assignments, and we prove by induction on the configurations in this space S refutation that in each for each configuration MI, there is a duplicator's assignment which has at most S variables in the domain, and that satisfies MI, meaning it satisfies every clause. So for every clause in that configuration, right? Remember that a configuration is a set of clauses, right? So if this is MI, then for every clause here, the assignment will contain at least one satisfying literal, and it stays small, which is important, right? We're going to use this to make the induction go through. So if we make the induction go through to the end, to MT, sorry for this Blackboard bold, it's just a leftover for different notation. So if we reach MT and we maintain this premise, we get a contradiction, because we can't have an assignment satisfying each clause in the final configuration, because the final configuration is just the empty clause, which is unsatisfying. So all that we need is to make sure that the induction goes through. And if you think about it, everything except axiom download is completely trivial. Well, if you delete a clause and you satisfied everything, you still satisfy everything by the same assignment. And if you use resolution, then the premises are already on the board, so they're both satisfied. That means that the conclusion of the resolution rule must also be satisfied. So you don't have to do anything other than in the case of axiom download. And in the case of axiom download, we use the property that our current assignment has size at most S. So we have a buffer of K until we reach the maximal size of assignments that the duplicator has. So that means the duplicator can extend this assignment to set every variable appearing in this clause of F that we have downloaded, because there are just K variables in it. And since you cannot falsify the clause by this procedure, because no assignment in duplicator's family falsifies F, then that means that duplicator actually satisfies this new clause. So we can keep just one variable, and therefore satisfies all the clauses in MI+1. There is one potential slight issue, namely now the assignment has size S+1. We kept one extra variable, which is potentially problematic if you continue incrementing the size here, but we don't, because the configuration MI+1 only contains S clauses. So to satisfy it, we only need one variable per clause. So we can trim the assignment down to S, and that's it. That's a contradiction. That proves the space that we're bounded by width thing. Okay. So people were also wondering, this notion of space doesn't make too much sense for very, very strong systems, unless it's total space, unless you count all the symbols, because for strong systems you can always take a conjunction of everything that's on the board, and that's going to be one formula. But for relatively weak systems beyond resolution, like for polynomial calculus or PC with resolution, just to remind you, this is the system that operates with polynomial equations over a certain field. The lines are polynomials, and we take them to mean that the polynomial is 0. And you can add two polynomials, or take any linear combination of two polynomials that preserves being 0, of course, multiply a polynomial by any variable. You assume as an axiom Booleanity of the variables, so x squared minus x is assumed to be 0 for any variable. And in the version that simulates resolution, the more reasonable version, you also have a formal variable negated x bar for every x, and you just have this additional complementarity axioms that tell you that x and x bar, they're both Boolean, of course, and they sum up to 1. So exactly one of them is going to be 1. So we can define space in PCR in more or less the same way as for resolution. we describe the refutation as a sequence of configurations. Each configuration comes from the previous one by either doing one inference and writing the conclusion on the board, or deleting something, or writing down a clause of F, or our axioms, our initial formulas. But there is one other thing, namely a configuration in polynomial calculus is a series, is a list of particular proof lines, and the proof line is a polynomial. So a configuration is essentially a list of polynomials. But to count space, you treat each monomial within these polynomials as one point. So that's going to be a lower bound on the total space as a number of symbols, and that turns out to be a theoretically somehow useful measure, like the best of both worlds. It gives meaningful lower bounds as opposed to just counting the polynomials, but it is weak enough to that you can get some lower bounds, and it's easier to work with than just counting the symbols. So we'll count how large blackboard space is being used by counting how many monomials there are in total in the polynomials written on the board at any given point. Okay. And yeah, the space of a configuration is the largest number of monomials appearing in any configuration. The space of a proof of a refutation, sorry, and the space needed to refute a formula is as usual, minimizing over the space of refutations of it. Okay, so it's very similar as resolution, but we're not counting clauses on the board, nor are we counting polynomials, just one per polynomial, but we're counting the monomials. Okay, so that's kind of funny. This thing is not very well understood. I mean, there are a number of results. Quite a few lower bounds have been proved on specific formulas, but a general understanding has been a long time in coming. So, for instance, there is like a very, very poor man's separation from resolution space. It's like by some sort of factor, like 4/3, and it uses artificial formulas and really takes advantage of some technical aspects of the definition of space. So technically, it could even be like resolution space, although that would be a surprise, but it's not known. And people were wondering, since you have this result that that space is lower bounded by width in resolution, can you have something analogous for polynomial calculus? And the answer, well, one possibility was that the right notion to consider instead of width is degree. So, of course, a polynomial in polynomial calculus has a degree, or it's a polynomial, right? And degree is kind of the notion corresponding to width when you move from resolution to polynomial calculus. If you take a clause that has k variables, so it has width k, and you translate it to a polynomial, that's going to be degree k polynomial. And like the width size connection for resolution, there is a degree size connection in polynomial calculus, which was actually noticed earlier than the width size one. It was like the model for the width size one. So also, typically, when you get width lower bounds for resolution, if the formula remains hard for polynomial calculus, then you might get a corresponding degree lower bound, and so on. So degree is kind of like the notion that you would expect here. So people were asking whether space in polynomial calculus can be lower bounded by degree. And it turns out, I'm a little bit worried that I might be using a slightly older version of my slides. And it isn't the case, sorry. So I will switch. I apologize. I was changing the slides all the time. Let me open up something that's, yeah, I apologize for that. So one further comment that I wanted to make of this was that one further comment they wanted to make on this was that there is also a slight connection known on between space in polynomial calculus and width in resolution, although it required changing the formula. So it turns out that the space of refuting a formula where you take every variable and replace it by a XOR of two fresh variables, and then rewrite that as a series of clauses, then the space needed to refute that in PCR is lower bounded by the width and resolution needed to refute that formula, the original formula. So that also made people wonder whether there's some sort of connection between PCR space and even resolution width for one and the same formula, although this here didn't suggest it very strongly, because clearly in passing from resolution to PCR, you are making the formula somehow more polynomial-like. So maybe this wasn't all that surprising. And now recently, we were able to prove with two colleagues, Nicola Gallesi and Neil Fappen, that there is a connection between polynomial calculus space and resolution width. Yeah, not just degree, but even resolution width. Although it's so far not clear whether the connection is tight. Namely, you may remember that if a formula has a resolution refutation in space S, then it has a resolution refutation with essentially S, just plus the width of the formula. For PCR, the change is quadratic. There is also a constant 4 here, but that will just be an artifact of this proof. You can get rid of this constant of the proof I'll give. So it turns out that if a formula has a PCR refutation that has space S, then you can refute it in resolution using width basically S squared. Plus you need the K to for the width of the original formula. So basically, space in polynomial calculus is lower bounded by, we don't know about the width, but we know that at least by the square root of width, which is interesting because these are two different proof systems, right? We're comparing not only two different notions of complexity, but you're lower bounding one for a stronger proof system in terms of one for a weaker proof system. So now the plan would be to switch to the board and prove this. That's going to be our main aim for today. Any questions about this so far?
No questions, I think.
Shimon, you don't look like you have a question.
No.
Okay. So let me stop sharing this and move to the board. Okay. So we're going to prove if F is a KCNF. Has PCR refutation in space S, then it has resolution refutation in width. And we're going to work with this 4 here, optimizing the multiplicative constant A. We'll do it this way. So assume not. So what is we have M1 through MT PCR refutation in space S, and that's one thing that we have, and the other thing that we have is a winning strategy, say H for duplicator in the forest squared plus K tabuli. Again, as before, we'll think of this, we think of H as a series of assignments, as a family of assignments. We think of H as a family of assignments. So let me, before we get into the nitty-gritty, let me mention a potential difficulty. So potential issue. We would like, that would be the neatest, and that would, if you could really work, it would potentially give a linear upper bound on the width needed to refute F, not just quadratic in terms of the space. We would like to do something like the Atzerius-Dalmau argument. Go down the refutation M1 and T, satisfying each MI by a small assignment from H. Okay, so here's an issue with this. Here's what a pretty complicating problem arises. So problem in resolution, if a space S configuration is satisfiable, you only need S bits of an assignment to do it, to satisfy it. One per clause, right? I mean, the space S means S clauses, and you just need one clause per assignment, one variable per clause to satisfy the configuration, if it's satisfiable at all, of course. In PC or PCR, it doesn't matter. That's not the case. If you look at just a single polynomial, 1 minus many xi's, okay? This thing has space too, okay? But you need n bits to satisfy it, okay? So to make this satisfied as a polynomial, meaning to make this 0, you need to set each xi to 1. But you need x1 becomes 1 all the way to xn becomes 1 to do it, to satisfy it. Okay, so this is a problem. It's kind of unclear how much whether you can somehow go through the refutation and maintain a small assignment that satisfies each configuration. So generally, this sort of trimming down argument doesn't work. Even if you kind of immediately redesign yourself to allowing quadratic size assignments, so a square or something like that, still this idea that you will take a configuration, satisfy it, add some more stuff to satisfy the next configuration, and then trim the assignment down to keep it within space S or even S squared, within assignment sizes or S squared, that doesn't seem to work. So there's a difficulty here. And a solution, sort of unexpected, I would say, is to introduce the following concept. Definition. So for a term, I'm always confused by which is term and which is monomial. So I will take term to be, say, variables, xk, and monomial is a x1, xk, where a is a field element. I've seen both conventions used, so it's not a big difference for us, but we'll make these distinctions because a term is a purely Boolean object, and monomial adds the algebraic stuff in some sense already. Okay, so for a term the t, we will say, I will say how you read this notation in a moment, but rho strange symbol t equals 0 if rho sets some variable in t to 0. So rho makes t 0 if it makes a certain variable. That's perfectly legitimate, right? The less trivial case is, well, a term can only have value 0 or 1. So our definition of when rho makes a variable 1 is going to be different. It's if there is no sigma extending rho, but still within the family, which makes t 0. So if you stay within duplicator's family of assignments, there is no way of making the term 0. So there's no assignment extending our rho that would be okay for duplicator and that would set a variable in t to 0. Then we say that rho makes t 1. Okay, and now the official term for this is forces. I'm not sure how many of you have done whether any of you have had contact with, say, forcing and set theory, the kind that you do to build a model of negating the continuum hypothesis, for instance. That's co-enforcing, but there you do more or less the same thing, but in a much more complicated, technically much more complicated fashion, of course. But the idea is that you are adding a new set of natural numbers to a structure that satisfies the axioms of set theory, and you only see this set as you only view it through finite approximations to its characteristic function. So you only see finite pieces of the set at any given point. And an existential property, here this would be exists a variable that's made 0. An existential property is forced if a finite piece of this set that is going to appear at the end already witnesses this existential property. But a universal property is forced if there is no way to extend a given finite piece of the set that you're going to add to making the existential property true. So forcing universal statements or negations of existential statements is done exactly like this. And surprisingly, or not that surprisingly, I mean, this sort of thing has appeared in proof complexity before, but never in quite such a context. This turns out to be helpful. So in either case, we say that rho decides t. And now we're going to extend this notion. We will want to treat this as a sort of truth value of the term under the assignment. It will turn out to have some strange aspects, but not completely strange. So we will try to understand how much of it is reasonable and how much isn't. So we'll generalize this to polynomials and to entire configurations. So for a polynomial p, and p, let's say it's the sum of aj times tj. The tj's are terms, the aj's are constants from the field. We say that rho, let me try to maintain this distinction between rho and p. So rho forces p to 0 if rho forces each tj to some value bj. So if rho decides every single term at being in the polynomial, and the sum if you really plug into the polynomial that supposed value of the term according to the forcing relation, that's going to be 0. So that's, rho forces the polynomial to be satisfied, and rho forces the polynomial to be unsatisfied, meaning non-zero. Well, the same thing. It has to give a value to each term in the sense of forcing. And then if you take that value seriously and sum up the monomials in the polynomial, then you get non-zero. Okay. And finally, we still have that to generalize that to configurations. So for a configuration, so that's a list of polynomials, configuration M, rho, like a blackboard state in the argument, rho forces M to true if rho forces each polynomial P appearing in M to 0, and rho. Can you guess what the definition of rho forces M to false will be? This is, I think, not completely or immediately obvious. It's not. Let me see if anybody has any intuition about this. When would we like to say that rho makes sure, in this sense, that we will treat a configuration as false? Well, okay, so it's the important thing is that you want to decide each polynomial. So rho decides, meaning sets gives a value or forces each polynomial P of M to a value, but at least one of them for at least one P rho forces it to non-zero. The important thing is that you do decide each polynomial. So you decide whether each particular polynomial is 0 or non-zero in forcing a configuration to be false. You might not assume this, but that complicates stuff technically, I guess. So rho decides P or decides M defined in the natural way. So you decide a polynomial or you decide a configuration if you force it to a value defined in the natural way. So any questions about this definition? We will have some examples. I will have one stupid example for when it works badly in just a moment. And then we'll have some further examples on the way, but maybe you're wondering about something. Okay, so let's first do an example which shows you when this goes wrong. Okay. So essentially, we would like this to behave reasonably well as a truth value. This notion of forcing. So let's say that if we have a configuration that already maxes out the number of variables that we're allowed to have in the domain, right? This is the max allowed in H. And let's assume that we have a variable that's not in the domain. So what does rho do to the complementarity axiom? I treat setting x and x bar as the same thing. I mean, setting x to 0 is the same thing as setting x bar to 1 and vice versa. But what does rho do to the complementarity axiom if it's for a variable that's not in the domain and rho doesn't have any more space in the domain? Well, let's see then. What does rho do to this term? It is not in the domain, so x is not set to 0, it's certainly not forced to 0, because rho doesn't set x at all. But moreover, we can't extend rho and set x to 0 within the family, because we can't extend rho within the family at all. So x is actually forced to 1. But strangely enough, the same thing is true for x bar. We don't set x bar, we certainly don't force x bar to 0 because we haven't set it, but we can't set it anymore by extending rho because there's no proper extension of rho. So this is set to 1 as well. So in general, the value that's forced for this polynomial is 1 minus 1 minus 1. That's minus 1, wherever minus 1 is in the given field. It's certainly not 0. Okay, so even though this is an axiom of PCR. Okay, so this is something that you're not very happy with, but it turns out that this is more or less the end of the bad news. Beyond that, mostly good stuff will happen. So this is a warning example, but it just tells you that you shouldn't come too closely to the boundary, the size boundary of duplicator's family, because if you do, you're potentially in trouble. But it turns out that most other things work neatly. So now let's for various bits of good news, pieces of good news. First, let's make some trivial observations. If we have an assignment in the family, say sigma, and that extends another assignment, say rho, and rho forces whatever it is, then sigma forces the same thing. So forcing is always preserved under extending an assignment. This is just by definition. If you set something to 0, you set something to 0. If you set it in rho already, then you have set it in sigma as well. If there is no extension of rho doing something, then there's certainly no extension of sigma doing something. That's the case for forcing a term to 1, and then you just generalize it in an automatic way to polynomials and configurations. So forcing is preserved under an extension. Also, for any configuration mi, we can't have rho forces mi and rho forces not mi. So at least that much is working for us, and that's again by definition. Like rho, sorry, I messed up the notation. That was obvious. What I wanted to write here is rho forces not mi. So not forces, that's trivial, but what I wanted to point out is that you can't force a configuration to both true and false. And that's again essentially by definition, because this says you decide each polynomial in the configuration and you set it to 0, and this one says you decide each polynomial in the configuration and at least one value is forced to non-zero. So these are clearly complementary. I mean, they're not complementary, but they're contradictory. It might be the case that neither happens, of course, but can't have both happen. So actually you get something much stronger. So here is the crucial, or one of the 2 or 3 crucial pieces of good news. This behaves well with respect to rules of PCR. So at least if rho is not too big. So if rho is below 4s squared, so k variables away from the limit of the size limit for the duplicator's family, then if there is no I, so if there's no line in the configuration, in the refutation, such that rho forces mi and forces not mi plus 1. Okay, so inferences in PCR, seen as a configurational proof system, are sound with respect to forcing by assignments that aren't too big. So this requires a proof, but it's not very, very hard. Okay, you just check the rules. Check the rules. Deletion and axiom deletion is trivial, of course. That's one thing that we have to check, right? I mean, if we just deleted something from MI, then actually it will remain forced in MI plus 1 will remain forced to yes, to true. It's a smaller set of polynomials. Axiom download. This will be pretty much like in the case for resolution. Okay. If MI plus 1 is MI union C, C is a clause of F of our formula that we're refuting. We can extend rho to set all variables in F, getting sigma. Why can we do that? Because rho is small enough. Okay, so we still have k variables to of freedom, and clauses only have k variables. Then sigma has to force PC equals 0. PC is the polynomial translating clause. PC is the poly translating scene. Because you never, no assignment in duplicators family falsifies a clause of F. So we've set all variables of it. That means we satisfied it. Yeah, so this should be like this. Yeah, actually, it's not directly a clause; it's a polynomial here already. So sigma has to force the clause to true, the polynomial translating it to 0. So sigma actually forces mi plus 1, because that's the one new polynomial in mi plus 1. All the other ones were forced to 0 already by rho. Therefore, rho does not force not mi plus 1, because if it did, then sigma would also force not mi plus 1, and that doesn't happen. So that's axiom download. Inferences, there are two slightly non-trivial cases of inference in polynomial calculus here. So complementarity is one. Complementarity. So if mi plus 1 is mi union 1 minus x bar, extend rho to sigma by setting x. We can do that. We're away from the size upper bound. Then sigma in particular satisfies this formula, so this polynomial, so it forces the entire configuration to true. So rho doesn't force it to false. This is like an easier version of axiom download. We only have to set one variable. We no longer bump into the problem that we had if we had rho at maximum size. And multiplication is the other one that needs, well, just a slight discussion. So assume that we have P in MI, that P is the sum of AJ, TJ. And let's say that MI plus 1 is MI union XP. We have added P multiplied by a variable. Now there are two cases. First case is you can extend rho to sigma, well, within the duplicator family, which sets x to 0. Okay. Then clearly sigma forces everything in mi+1 to true, so rho doesn't force it to false. And the other case is that you can't. There is no way to set sigma to 0. No, to set x to 0. Not case 1. Then actually, rho already forces x to equal 1, and then it also forces, and for each tj, a term in our polynomial p that was already present in mi, so each term is forced to a value by rho. There is bj such that rho forces tj to equal bj, and rho also forces xtj to equal bj. It's going to be the same value. If some variable in tj was forced to 0, this is going to be 0. If everything in tj, if tj is forced to 1, then this thing is also going to be forced to 1 because we can't make set 0. So since rho forced p to 0, we also have rho forces xp to 0, and that's it. We're done. And therefore, rho itself forces mi+1 positively. Okay, the other cases are easy. Okay, other cases. Immediate. There is no working it. And that's the end of it. So this is a pretty crucial thing. Okay, this turns out to work. Now, there's another useful lemma that's a poor man's version of this fact that you can, that's one of the poor man's versions that we need of this fact that you can, in resolution, satisfy a small space configuration by small size assignment. This is called the deciding lemma, or it's called deciding lemma for the purpose of our lecture today. For every row in H and every I from 1 to T. So that's a number of our configuration. There exists an assignment in the family extending row by at most s bits. There's a less than or equals here, which decides this configuration. Decides. We don't have control in general on whether it decides it will be true or false. So we don't know to what value, to what truth value, the configuration will be forced by sigma, but we can at least force it to a truth value. Okay, by setting just a few bits in row. So why is that the case? Well, the point is essentially that there are not that many monomials in mi. So there are not that many terms. So for every monomial, say mj equal to aj tj appearing in the configuration, extend, if possible, extend well, the current row by just one bit. To force TJ to 0. If you can, then you just extend the current assignment by a single bit. Otherwise, the current assignment already forces TJ to be 1. So by looking at each monomial in the configuration and looking at the term living within that monomial, you do one of two things. If you can, you extend your original assignment row just by one variable in the domain, and in that way you make the term 0. If you can't, the term is already forced to 1. So once you go through all the terms, and they're just S terms, you have decided each term. Once you go, after going through each TJ, and J is 1 to, well, at most S, we don't know what the exact number is, all terms in M, and therefore MI, and therefore MI itself, therefore MI itself are decided. Okay, that's it. So that's a sort of locality lemma, but a weaker one than in the case of resolution. So we know some basic stuff, and now it's kind of unclear what to do from this point onwards to get a contradiction from our data, from having this duplicator strategy and the small space refutation in polynomial calculus. And roughly what we're going to do is that we will gradually extend within our duplicator family an assignment starting with the empty assignment. We'll extend it, not too many times by not too many bits at each step. So we will stay within the family. That's going to be important. And we will eventually focus on a smaller and smaller interval in the proof. I'll draw a picture in a moment. In such a way that this assignment makes, well, the behavior, that assignment somehow with respect to its behavior on all configurations within a certain interval of the proof gets, in a sense, ever more and more complicated. And eventually, there's going to be a measure of sort of complications, not quite that, but sort of. And eventually, it's going to be so complicated that that gets a contradiction. Okay? And you need a measure of this. Well, complication is not a really good term, but you need some sort of measure of progress that you're going to be making within understanding the refutation of your working towards a contradiction. And the measure that turns out to work, there is some sort of complicated story behind it, and it's not very easy to give an intuition, but the measure that turns out to work is the following. NZ stands for non-zero. So NZ of MI in the row is the set of those terms, say TJ, appearing in MI, that are not forced to 0 by row. So if you look at an assignment in duplicators family, and you look at a configuration in the small space refutation, you look at how many or which terms have been set to 0, and you then look at the set of those that aren't. They might be forced to 1, they might be undecided yet, but they're the ones that matter. They're still, in some sense, alive. And there's a special notion to use here. So rho guarantees m non-zeros in mi. This means the following thing. If for every extension of rho, sigma, within the family, well, let's not write so much, this one. That extension, sigma, will have still many non-zeros. Is at least n. Okay, so it's a strange notion. I would try to. It somehow came from our original attempts at trying to understand some really simple cases in which each configuration was just a single polynomial, and then over F2, a polynomial is set to true if an even number of terms is 1. And it's not true if an odd number of terms are 1. So we kind of went like, well, maybe at the beginning there's the empty assignment, there's the all zeros assignment that makes things 0. That's a way of making a polynomial true. Then if you have at least one term that's non-zero, then you must have 2. And if you have more than 2, then you must have at least 4, and so on. So somehow this eventually came to be. I'm not really able to give a perfect intuition of why this works. And here's the main lemma, which we'll have time enough to sketch. We'll first derive the result from it, the contradiction, and then we'll prove the main lemma. So for each m that's smaller than s, there exists a row, we could call it rho m, within a duplicator's family, and there exist numbers ij. Those are numbers of configurations. So I is greater than 1, j is greater than I, j is below t, with the following properties. Firstly, rho m forces mi to true, and rho m forces mj to false. Secondly, rho m guarantees m non-zeros in each of mi up to mj. So in this like proof interval, as you could call it, there are going to be lots of non-zeros according to each assignment extending rho m. And finally, rho m is not too large. At each step, we extend it by at most s, at most 4s. So we have this one. So the picture would be like this: that we have m1 here. There's mt somewhere at the bottom. And somewhere in the middle, there's an mi and mj. This is mi, sorry, this would be mj. So we just narrow down our focus to just look at this interval. So rho believes this guy is true, rho m. Rho m believes this guy is false. And in the middle here, like lots of non-zeros here. Lots of non-zeros here. According to rho m and any extension of rho m. So in a moment, I will show you, I'll tell you why this implies a contradiction once we get to S. But before we begin, of course, we're going to prove this by induction on M. But I would like to ask you, why is the base step true? So why is this true for M equals 0? Hint, do you remember what M1 is and what MT is?
1 and S?
So M1 is the empty is the empty configuration. There's nothing in it. So it's automatically forced to true, right? There's no way of forcing it to false because there's no polynomial in it. Each polynomial is forced to 0 because there's no polynomial here, right? So this one, any assignment trivially forces this guy to true, okay? And MT is a one-element configuration that just contains contradiction. Contradiction in the case of polynomial calculus is the constant polynomial 1. I forgot to mention that perhaps, or to remind you of that, but that's how polynomial calculus works. So this is just, yeah, this is actually the empty set. And this is just the single polynomial 1. So this is always forced to false because there's no way of making this polynomial true. Okay, so any assignment forces this guy to true and this guy to false. So what is our assignment row 0? This is actually determined by the conditions of the lemma. What is our assignment row 0? You can look at condition number 3 in the lemma. Let me spoil all the remaining fun for you. Well, M is 0, so row 0 has to have 0 variables in it. It has to have domain size 0, so it's empty. Okay, so row 0 is simply the empty assignment, and the empty assignment makes the first configuration forced to true, the last one forced to false, because these guys are trivially forced to true and false respectively. So condition 1 is satisfied, and guaranteeing at least 0 non-zeros. This is monotone or anti-monotone lemma. Everybody guarantees at least guarantees 0 non-zeros. That means, just for any extension of the empty assignment, the number of non-zeros in that extension will be at least 0. Again, that's trivial. Okay, so the base step is automatically satisfied. So let's discuss why this leads to a contradiction. Okay, so proof of contradiction from main lemma. Take the maximal possible m, S, okay? Then for each k in the interval between I and j, the one corresponding to m, rho S decides mk, because mk has at most s terms, but the number of non-zeros of rho m in mk, if I turned the arguments around, I apologize for that, must be at least s, because rho m guarantees s non-zeros in these configurations here. So each term in mk is forced to 1. But that gives a contradiction. But rho m forces mi to true, rho m forces mj to false. So if each of them is forced to a value, each of them is decided. So there is k somewhere between I and j, such that rho m forces mk and rho m forces not mk plus 1. At some point, we must switch from forcing true to forcing false. This contradicts soundness. Okay, so I've got about. Is this argument clear? It's possibly more important than the technical details of the main lemma, but I will want to say something about it. Okay, if I ask whether the argument is clear, I won't get any response, of course, but I'm afraid that if I ask if the argument is unclear or whether anything specific in it is unclear, I won't get any response either, but let me try that. Is anything unclear in this argument? Okay, then. I'll assume it's fine, and we'll discuss the main lemma. We'll try to prove the main lemma a bit. Okay, so the proof of the main lemma, I want to go back to the presentation for the last 3 minutes or so. So let's do a 10-minute sketch of this. The proof of the main lemma is kind of as follows. So base step for m equals 0, we have discussed that already. Rho m is the empty assignment, I is 1, j is the last configuration. That's the contradictory configuration. So now the induction step. So assume the lemma holds for m, where m is smaller than s, so we haven't reached s yet. Okay, let rho m be given by the statement for m, by the induction thesis for m. Oh, and let's say that I and j are also given. Okay, so we've got I here, we've got mi here, mj here, and now we don't really care about what happens above and below this. This stuff we kind of ignore. We build rho m plus 1 in 2 half steps. So the induction step splits into 4 quarter steps, because each half step will also split into 2 things. First, we will increase the increase I to some I prime that will be somewhere between I and j. It won't be j, it will be definitely smaller than j. And then we decrease j to some j prime that's strictly greater than I prime, but stays above j. So we'll get some I prime here, and then this will be mj. At the end, we'll have the new I becomes I prime, and the new j becomes j prime, and we'll find rho m plus 1 along the way. So we sort of work separately on each side of the interval in this proof. We were going to shrink it and extend our assignment as we go along. So I think there's enough time to at least discuss the first half step. So we work on the top of the interval towards, well, I don't know, top or bottom, depends on how we draw it, but towards the beginning of the proof. You make a case distinction. Is there some index, let's say L, between I and j, such that an extension of our current assignment, say sigma, has the following 2 properties. Firstly, it satisfies that configuration of that number, ml, and secondly, it has the minimal allowed number of non-zeros. Okay, so recall that this is the minimal possible number. Right now, minimal possible number for an extension of row over row M. And configurations between Mi and Mj, right? We're guaranteeing at least that many non-zeros in everything. There are two cases. This can't happen. So at least with configurations near the top of the new interval, the ones that are going to force our configuration, they're going to be forced to true by our assignment, we would have a problem with having too few non-zeros, because remember, we want to guarantee n+1 at the end of this induction step. In that case, we'll just put I prime to be equal to I. So this is, we're not going to change the top of the interval. And our first half step towards constructing row m+1 is actually done. This will simply be row m plus half will be row m. The second case is where we do work. Okay, so then so we have a potentially problematic configuration. There's some ML and some extension of row m that makes ML forced to true. It has fewer non-zeros than we would like. Then take corresponding sigma and take the last L where this happens, or largest L where this happens. So beyond that L, there will be no configuration forced true by an assignment that sets few non-zeros, so that it has few non-zeros. And take corresponding sigma. And now here's a trick, or an observation perhaps. Take row n plus a quarter, we'll get to n plus half in a moment, which is greater than our current assignment row m. It's within this extension sigma, so it's somewhere in the middle, right? So this is mi, this is mj. This one already row says that this is false, row m says that this is false. Here row m already says that this is true. And here's the problematic one, ml. Sigma says that this is true. And sigma has few non-zeros. So take this row m plus a quarter between row m and sigma with the following properties. Firstly, it also forces ML to true. And secondly, it's kind of small. So it extends row m by just s bits. And this is non-trivial. We're going that such a thing exists. This goes beyond the deciding lemma, because we can certainly, in general, extend row m by s bits to decide this configuration, but there's no guarantee that will extend that'll decide the configuration in the same way that sigma does. So technically, it's not clear why we have such a small extension of row m forcing the configuration to true. But in fact, you can. So row m plus 1 exists because we can take just one bit from sigma minus row m, so from this kind of overhead that sigma has, for each term, for each of the at most s terms in ML, that are set to 0 or forced to 0. That's the same thing for setting to 0 in sigma. The other ones there actually, we know exactly how many there are of them. There are the other terms, there are m of them, the other terms. There are exactly m of them, must already be forced to 1 in row m. The point is that row m has the fewest possible number of non-zeros, because even sigma has so in row m plus a quarter. Let's make this. We couldn't add anything else to row m plus a quarter. This is illegible. Let's correct this. We couldn't add anything else to row m plus a quarter to force a new term to 0, because then we would be left with just m minus 1 non-zeros and an extension of row m, and that's impossible. We're guaranteed to have at least m non-zeros here. That's how this notion of guaranteeing non-zeros, that's the sort of work that it does for us. That it lets us, given an assignment extending row m to the true value we want, take a small sub-assignment that keeps the same true value first. And that's more or less done. Okay, so now by deciding lemma, add at most s bits to row m plus 1/2, or a quarter, getting row m plus 1/2 that also decides the next configuration, ml plus 1. By soundness, row m plus 1/2 has to force ml plus 1 to true. It can't force it to false. So by maximality of L, the number of non-zeros of Rm plus 1/2 in ml plus 1 will be at least m plus 1, because you can't have just m. That would contradict the maximality of L. And we're halfway through. I won't do the other half, but it's kind of similar. So the second half step. And we set I prime to be L plus 1. So this is the place where satisfying assignments will have at least m plus 1 non-zeros. So then the case distinction is there a number L between I prime, the new beginning of the interval, and the current end, which is the old end, and sigma extending our halfway point assignment such that it will no longer satisfy the configuration, it actually will falsify it. If that is exactly m, and we do something similar, It's pretty symmetric. It's not entirely symmetric, because there is a sort of difference between the true values, but it more or less works out the same. So yeah, that's the end. So that's how you get this. That's how you get this lower bound on PCR space in terms of resolution width. And now let me go back to the PDF, if I may, again, occupy you for 3 or 4 more minutes and finish up the the lecture. So what comments do I want to make about this? Firstly, you may have or may not have noticed that this proof doesn't have much to do with polynomials, with the specific rules of PCR. The important thing is that you have to work with a proof system for which has sound rules. I mean, semantically sound. It preserves true value in the usual sense of formulas. And secondly, you should be able to see each line. A line in this description of PCR was a configuration, so it was S monomials. It should be a Boolean combination of at most S terms. So where a term is basically a conjunction, it tells you what the true values of finitely many literals are. So this works for a much more general definition of proof system, which kind of explains how you can get lower bounds in terms of resolution on a proof system that talks about polynomials. So it's not about the polynomials, really. It's about more general features that this particular system happens to have. So the second point I wanted to make is optimality of this construction. It's not at all clear. We're doing strange things here. And it's definitely possible. I mean, it's consistent with our present knowledge. It's open that perhaps space in polynomial calculus is, well, it can even be linear in resolution space simply, but lower bounded linearly in resolution space. Then it would mean that it's lower bounded by resolution width. That's an open problem. We have no idea what the answer is. It's maybe worth mentioning that there are some particular formulas where people worked hard to get a combinatorial lower bound on PCR space. And there's a resolution space lower bound which is linear. And you kind of would expect that the PCR lower bound should be linear as well. But what people can get with a lot of effort is square root. And we actually get the same result with less effort, with just this logical argument. But the square root appears again. So people kind of worked, tried to do it completely independently from this construction, and they got the square root. So maybe the square root is there for a reason. We don't know. And one final point that I wanted to make specifically about space. So this is not a general discussion of what we didn't cover during the lectures. We covered very little, of course. But one specific point about space and these three measures that we considered in general, space, width, and size or length, which is pretty much the same thing in resolution. There's a whole big area where people study trade-offs. So we have a number of results like, if you can minimize this measure, then there's another proof minimizing another measure or making another measure small. And there are lots of results that tell you that you can't minimize both. So for instance, there might be a formula that has small width refutations, small space, but you can't have both at the same time. I mean, there are some cases due to Rasborov recently. Perhaps it's about the size, where he proved that if you want to optimize one of the parameters, I guess it would be space, perhaps. I'm not quite sure. I'd have to recheck that. Then that causes the size to become doubly exponential, even though there's always a single exponential proof of any formula. But there are these even super critical trade-offs that optimizing one measure causes the other measure to blow up below the worst case lower bound in that measure. So such things happen. We didn't cover that. Last thing, if you want to know more, I would recommend books. There is a recent textbook by Leszek Kołodziejczyk on proof complexity that came out last year, and it emphasizes the more logical side. So this is for somebody who likes logic. For people who would be interested more in the purely set-solving side, the practical side, I think the Handbook of Satisfiability, the second edition, is just about to appear or has just appeared, and Chapter 7 of it is a more than 100-page survey of proof complexity by two serious experts. So it's a potentially great read. I know because I read like 80% of it preparing for this course. And finally, let me spread the word. I got news recently that a number of workshops at the Simons Institute this semester because they're happening online, they're going to be open to more or less everybody. So you can go up to that web page, and if you're interested, register for them. And there is some stuff related to proof complexity, mostly on the SAT solving side. There are lots of workshops and events and ongoing special semesters about SAT coming up at the Simons Institute, and maybe some of this will be interesting for some of you. So let me say thanks for coming, for persevering until the end, to those few most faithful of you. There's still class coming up, but this is the end of the lecture, so thanks a lot.
Thank you, Leszek, very much. It's a very nice overview of the area, and I think many of us have learned a lot.
So I'm not sure if it counts as a true overview, because I essentially excised all the non-trivial combinatorics from these lectures, right? I mean, I could do some of it, but it would take me more time than.
Yeah, well, that's then an overview in a way. So we resume at 12:15, right?
Right. So see you then.
See you then.